Welcome to EPG Pachala. I'm Dr. Venu Satini from the Department of Philosophy, University of Hyderabad. This is Logic 1 and the name of the module is Basic Set Theory Part 2. The module is written by Professor Mamata Bandyopadhyay. Last time we have discussed the possibility of constructing sets and then operation of sets, relation of sets, and then went on to define something called ordered pairs or couples, which is defined by Cartesian product. We want to go a little further today and exclusively see the relation which holds between members in the set. In that we will explore different properties of relations. Also, we know that relations, which we have seen last time, is a special kind of set only, because we do some kind of set operation to generate new set, and we are doing Cartesian product to generate this set. So it's a set of relations. In this sense, we can also use those set operators like union, intersection to define even on relations. So today we'll explore all these operations and properties of relations, and then from there we go on to a very special kind of relation called function. Now we know how to define a relation. That is, given a set A and B, we can define a Cartesian product of A into B and then come up with a list of ordered pair. Today we will talk about something called Converse relation. Converse relation is a relation such that if there is a relation from A to B, then we will define a relation from B to A. In other words, given any two elements x, y, if there is a relation from x to y, converse relation will be y to x. So the order is important. Let us look at a board, for example. If R is a relation and it has a set of members which are all ordered pairs, one is 1, 2, 2, 4, 3, 6, and if we define converse relation on R, there is a small mark above R. Sometimes it is a bar R or sometimes it's a complement R, but let us say it's converse R. So converse R will be 2, 1, 4, 2, 6, 3. You see the sequence have changed from 1 to 2. In the converse it has become 2 to 1. Just change the order of the pairing. That's how we get this idea of converse relation. Now we can get new and new kind of relations by doing certain things, and when we want to talk about two kinds of relation to define some relation, let me come up with an example. If suppose somebody is known as a grandfather and somebody is a grandchild, how are they two related? They are related through father. So that will give us the idea of combining two relations at a go. Father, the idea of grandchild or grandfather. Likewise, this idea is called the relative product, means a kind of composite or combination of relations. Here we will call it binary relation, R and S. But we should always keep in mind that relation is always defined in a set or on a set. So let us look at the proper definition of what is a relative product. The relative product of two binary relations R and S, represented by R oblique S, holds between two elements X and Y with double condition, that is, if and only if there is an element Z such that there is a relation which holds between X and Z and another relation which connects Z with another Y, then only we can talk about the relation of X and Y. So put it in logical symbols. It is X is related to Y via two relations RS even only if there is an element Z such that X is related to Z and also Z is related to Y. Suppose, let us look at the example. If there are two relations, P and R, and P having this number of ordered pairs 2, 4, 3, 6, 4, 6. Another relation R with members 3, 2, 3, 4, 5, 7, 6, 9. If we are asked to define these composite relations, means relative product relations, PR, then what is the set we are going to get? By definition, the first element should be supplied from the first element of relation P, and the second element should be supplied by the second relation, which is R. So how do we do this? Let us check one by one. Say 2. What is the second element? 4. Is 4 the first element of the second relation R? No. No ordered pair in the second relation starts with 4. Now let's go to the second one. 3 and 6. Now, is any element in relation R start with 6? Yes, the last ordered pair 6, 9. That means we got it. We can have a collection 3 via 6 to 9. So we have our first element 3, 9. Let's check the last one 4, 8. Any element in the relation R start with 8? No, it doesn't. So if there is a composite relation or a relative relation PR, we have only one. Now we can also define these kind of relative relations or relative product relation on itself, that is P oblique P. Can we do like that? Let us see. Given relation P, we have 2 to 4. Anything starting with 4? Second, no. Third, yes. 4 and 8. That means we can have an ordered pair 2, 8, because 2 to 4, 4, 8. Is there any more? No, there is not. That is the only one we can have. What about the second relation R? Can we have this kind of RR relation? We look at the member 3, 2. Anything starting with 2? See, no. We move on to the next pair 3, 4. Anything starting with 4? No. 5, 7. Anything starting with 7? No. 6, 9. Anything starting with 9? Look left and right. No ordered pair in this relation R starts with 9, in which case our collection is empty. It means null set or void or empty set, which is lambda. Now we talk about this kind of converse relation and let us say binary relations, where we use two relations to define relation of two entities via the third element. We can also talk about properties of relation. What kind of relation holds between two things will give us the property of such a relation, in which case there are n number of formal properties of relation, and we will explore them one by one. Perhaps in our ordinary conversation or language, we have come across words like reflexive or symmetric or transitive. These are actually formal definitions which have been given to us from set theory. So we'll begin with reflexive relation. What is a reflexive relation? It is a very technical, in the sense a reflexive relation is a special kind of relation, and the only example that I can give now is a relation with oneself, and that is identity. I am identical with myself, A. So but we know that relation is defined by Cartesian product. So if we have just one element of a set A, define a Cartesian product of A into A, we have ordered pair AA. So A is related to itself by relation of identity. In this case, this is reflexive relation. So let us look at the technical definition, how it is been defined for us. A relation R is reflexive in a set A. Note that it is always defined in a set, means between the members of a set, even only if every member of the set is related to itself. See, self-relation by the relation. R, technically put in symbolic language, is reflexive in A, even only if for all values of x, if x is a member or element of A, then there should be a relation of x and x related R. X R x, that means x has a relation. Now we can talk about a relation which is just kind of opposite of reflexive relation. How are we to understand that? That is defined as irreflexive relation. Technically put, we can see it like this. A relation R is irreflexive in a set, let us say A, set A, even only if no member of the set is related to itself by the relation. Let us look at the screen. R is irreflexive in A, even only if for all values of x, or for each x, if x is a member of A, then there cannot be any relation within itself. A is not possible. So let us look at some concrete example. If we have a set A having 3 members 2, 3, 4 and another set B having 2 members 1, 2, then we can define a relation on A. That means Cartesian product of A into A will give us these numbers 1, 2, 2, 2, 3, 2, 3, 3 and 4, 4. Another relation, let us say 3 relation 2, then we have 1, 3, 2, 4 and 1, 1. The question can be raised, is relation 1 R1 reflexive in A? Let us look whether it satisfies the condition, whether R1 is reflexive. What is the definition? For every member, let us say here every member is 2, 3, 4, there should be a relation such that it is related to itself. That means it should have 2, 2, 3, 3, 4, 4. In R1, do we have this one? First element, no. Second, 2, 2, yes. 3, 2, no. 3, 3, yes. 4, 4, yes. So R1 is reflexive. What about another relation? Let us say, what if we define relation R on the set B? In set B, that means, is it reflexive? Yeah, look at this one. Set B has 1 and 2. Do we have 1, 1 in relation 1? No. In other words, it is not reflexive. But is it irreflexive? That means it should not be related to itself. But we find that there is 2, 2. In which case it is also not reflexive. So we will say it is neither reflexive or irreflexive when we consider the set B. In other words, the relation like reflexive or irreflexive will be always understood or defined in relation to the set which we are talking about. So though the relation is same, relation 1, the properties change when we see set A and when we took a look at another set, set B. We go on to another property of relation which is called symmetry. And now symmetry is interesting because it often confuses us. For example, think about love. Love is a relation between two people, but is it symmetric? Our immediate intuition is to say yes, but love is not symmetric. In the sense, I may love a girl, but that girl may not love me. So relation, if I go out, it doesn't come back to me. And symmetric is defined like that. If there is a relation from A to B, there must be a relation from B to A also. So what about lovers? Yes, lovers are such that if A loves B, B also loves A. That's why they are called lovers. So lovers is a good example of symmetric relation. What about brotherhood? Brother. Temptation again is to say yes. For example, John is my brother, and I say, and if I am a brother of John, then John also is a brother of me. But think about a situation where there is John and Mary. John is a brother of Mary, but you reverse the sequence. Mary is not a brother of John, in which case it is not. So how do we understand this technically? Look at the definition. R is a symmetric relation in the set A, even only if for any two elements x, y, or for all x, for all y, if x is a member of A and also y is a member of A, and there is a relation. And so we will later on consider some example to explain this one, but before that, let us look at another related property which is called asymmetry. How do we define asymmetric? Again, let us look at the screen. It is being defined as a relation such that for all x and for all y, if X, Y are both members of A and there is a relation from X to Y, it is not the case. If there is a relation from X to Y, it is not the case. Then there is no relation from Y to X. Ordinary example again. Can we think of ordinary example which is asymmetric? I can give one. A relation between mother and child. There is a person, mother, that is a Sonia Gandhi, and then son Rahul Gandhi. Now, if I put Sonia first and then Rahul and then define a relation, it is one of motherhood. But if I put Rahul first and then Sonia later, it doesn't become motherhood. In other words, motherhood is asymmetric. You cannot define the same relation between these two even if there is a change. That this relation is one directional. It goes only one way, it cannot come back. That is asymmetric. We can go on to talk about another interesting property which is called antisymmetric, and it has been technically defined like this. R is antisymmetric relation in a set A or on a set A even only if there are two elements xy, and for all xy being a member of the set A, and there is a relation, let us say x and y, and also there is converse relation, that means y to x, then x is equivalent to y. In other words, we are saying x is related to y, y is also related to x. Looks like symmetric, but the condition says that if there is such a situation, then it should become equal. X should become equal with y. This is what distinguishes antisymmetric from symmetric relation. Can we think of an example? Actually, we have talked about subset relation. In which case, if A is a subset of B, B is also a subset of A, then we know that these are identical. So in which case they become equal, or even sometimes greater or less in number theory. It can become, or the better example could be equality. If a number 5 is equal to 5, again 5 is equal to 5, therefore 5 is equal to 5. So any equality is actually antisymmetric. Let us look at some examples. Suppose we have a set A with members 1, 2, 3, 4, another set B with members 5, 3, 6, and we have a relation 1. We have two relations, relation 1 and 2, and relation 1 is having these members 1, 2, 2, 1, 3, 2, 2, 3, 5, 3. And relation 2 is having these members 1, 3, 2, 4, 1, 1. Now, is relation 1 symmetric? Let us look very closely. If there is an ordering of pair like 1, 2, there should be another pairing of 2, 1. So, what are the members here? 1, 2, yes. So, can we reverse? Is there any 2, 1? The next immediately is reverse the sequence of elements. So, it's okay. Next one, 3, 2. Is there 2, 3? Yes. 5, 3. Is there 3, 5? But is 5 a member of A? No. That means it is immaterial. Only we need to consider which are members of a set A. And since 5 is not a member of A, we don't consider. In which case, this is considered symmetric. What about asymmetric relation? Let us take a look at set B and see whether we can define asymmetric relation on this with respect to relation 1. Asymmetric relation. So there are 3 elements, 5, 3 and 6. Is there any relation starting with 5? Yes, last one, 5, 3. Is there 3, 5? No. Anything with 3? 3, 2, yes. Is there 2, 3 relation? Yup. But again here, 2 is not a member of B, in which case we'll pass it. 6, anything started? No, 6 is not even occurring in the relation, so we rule out. In which case, when a relation R is defined on a set B, it becomes asymmetric. R2 is, if you look it properly, R2 is neither symmetric nor asymmetric, but antisymmetric in A. So also R2 is symmetric, asymmetric, and also antisymmetric in B. How do we define R2 on a set B? You see, look, the members of set B are 5, 3, 6. If we look at relation 2, there is no occurrence of 5 and 6 in the ordering of the pair. So in which case, if you look at the definition one by one, you will understand that it is symmetric, asymmetric, and also antisymmetric in B. Now we move on to the other property, which is called transitive. Transitive means trans, moving from one to another, transportation, that kind of thing. So that means we need three things. The other relation we are talking about may be understood in terms of two things, binary. But if we are talking about transitive, like from A to B and B to C, trans via something. So here we need three elements. And how are we to understand transitive relation? Maybe let us say ordinary example could be again the equality. If a set A is equal to B and B is equal to C, then we can also show that A is equal to C. So how are we to capture such a definition using set theoretic properties? Let us look at the screen again. R is transitive in a set A if and only if we need three elements, keep in mind, to define a transitive relation. X, Y, Z, for all X, Y, Z, all are members of A. X element of A, Y element of A, and Z element of A. And this is important, there is a relation between X, Y and also Y, Z. Then we can say that there is a relation from X to Z. That is a definition of transitive relation. Now keep looking on the screen. There is another property which is just opposite or different from transitive. It is called intransitive relation. R, a relation is intransitive in a set A even only if for all X, Y, Z such that they are all members of the same set A, and if there is a relation from X to Y and Y to Z, then there is no relation from X to Z. Now let's talk about ordinary situation. Is the relation of motherhood transitive? You see, A can be a mother of B, B can be a mother of C. Now is A mother of C? No. In other words, it is not transitive. There is a relation from A to B, motherhood, B to C, motherhood, but A and C, the relation is not motherhood. In fact, it is actually grandmother. So it is intransitive in a sense. As I mentioned before, any relation of subset will be transitive. In the sense, if A is a subset of B, B is a subset of C, in other words, A is also a subset of B. Or ordinary relation, let us say older. If I am older than John, John is older than, let us say, Mary, of course I am older than Mary. So this is called a transitive relation. Think about greater or less, or even greater relation in number. 5 is greater than 4, 4 is greater than 3, therefore 5 is greater than 3. It is transitive. So anyway, let us look at the concrete examples. Suppose we have a set A with members 2, 3, 4, another set B with members 5, 3, 2, and there are two arbitrary relations, R1 and R2, and members of R1 are 3, 3, 2, 4, 4, 3, 2, 3. Members of R2 are 1, 5, 6, 9, 7, 7. Then we say R is transitive in a set A as well as in B. How? Keep looking at the relation. In R1 there is 3, 3. So is there any ordered pair starting with 3? No. So then we finish. We go on to the next one, 2, 4. 2, 4. Any starting with 4? Yes, 4, 3. So we need to find a relation from 2 to 4. Yes, 2 4 itself. No, 2 to 3. The next one, next one. So 2 3 is there. We move on to 4 4 3. Any member starting with 3? Yes. The first ordered pair 3 3. So is there any pairing with 4 3? That itself is 4 3 itself is the third one. What about 2 3? 3 3 and then 3 3. So 2 3. That's how it is transitive. We are defining these properties with the help of material implication. It means condition if then. That means we will say yes only if the condition is satisfied. If. But if the part is not satisfied, then by definition, or we say vacuously, it is true or satisfied. So in R2, 1 5 is there, but no pairing is starting with 5, gone case. So default, it is satisfied. 6 9, no number is starting with 9, so it is also gone. 7 7, yes, but 7 7 is not a member of either A or B, in which case we cannot. So it is interesting to say that relation 2 satisfies both a condition of transitive and intransitive, even with respect to both set A and B. We have just seen three different kinds of different properties of a relation under the head of reflexive, symmetric and transitive. There is another relation about which I want to talk now. It is connectedness. What do we mean by connectedness? Here let me take a small example of a family. In a given family, everyone is related to one another. No member of a family is not related to anyone. In other words, everyone is related to one another. Say either it is brother-sister relation or son, father, or children, parents. I mean, no one in a family is without relation. Each one has a relation with each other. So this is called connectedness. Let us look at the technical definition. R is connected in a set A even only if for all x and y the condition is if x is a member of A, y is also a member of A, but x is not identical with y, then in other words, either x is related to y or y is related to x. Keep looking at the screen because in relation to this we can also define another relation which is called strongly connected. When it is so, it is so even only if for all x, y, both x and y are element of A. If they are element of A, then either x is related to y or y is related to x. What is the difference? In the first condition, that connectedness, we have a condition that x and y should not be identical. But in the second condition, which is strongly connected, we are not eliminating the possibility of same relation holding between two members. So in the first case, given any two numbers or on a number theory, the sign greater, we can always put it any two number is related by greater. You put it, you will always find yes or no. So it is connected because greater, we are not saying greater or equal. So it can be defined that way, connected by relation of greaterhood. Whereas in the second case, strongly connected, we can use equal or greater or equal or less, such that if I put 5 on the one side, 5 on another side, it holds good. So even if I change it, it holds good because they are the same number. So in which case greater or equal to or less or equal, or even in the language of set theory, subset is a relation of strongly connectedness. How is there a mechanism by which we can combine all these kind of relations in one relation? I mean, is there a possibility to talk about these properties, reflexive, symmetric and transitive in one relation? We say yes, and it is called equivalence relation. A relation is equivalent even only if the relation is reflexive, symmetric, and also transitive. How are we to understand this? I can give a small example. Identify a group of people and then classify this group of people according to their age. One group of people with the same age, let us say 5 years, another with 10, another with 15. In each class, in each group, you see A is related to B with the same age, let us say 5, and B is related to C with the same age group 5. So A is also related to C with the same. So it is reflexive because 5. Identical in the sense of age 5. Symmetric because the same holds good 5. Either way you change the relation, the relationship is still 5. So when we go on to A to C, from A to C, the relation, because it is same age, it holds good. So in such a case, it is true of the set of people with 5 years and 10 years and 15 years. I mean, in each set, if they are equal in their height or age or weight, I mean, equality, in other words, is an equivalent relation. We go on to the next topic, which is called function. Functions are a very special kind of relation. We have to look at it very carefully. It is also the result of a Cartesian product. In other words, relation is a subset of Cartesian product, and function is a subset of relation. So it is differentiated by a list of conditions. Relation, okay, but very special relation, that's why they are called function. Let us look at the technical definition before we proceed. A relation R is a function even only if for all x, y, z such that there is a relation from xy. I mean, xy is a relation of R, and also xz is a relation of R, then y is equal to z. Notice, keep looking at the screen. Notice that y and z are the second element of the ordered pair. X in both the occurrence is the first element of the ordered pair. In other words, if we are defining a relation from a set A to set B with members, then each element in the set A needs to be correlated with another element in the set B. Now the condition is such that no element in the set A can be related with two elements in the set B. The example I can give a very funny one, but you see, if I am a husband of a woman, then I cannot be a husband of another woman. Of course, I'm thinking of monogamy. So I cannot be related with two wives. In this case, given a monogamous society, a husband is not a function. Likewise, a mother is not a function in that a mother can have several children. So a mother, and then on the set B is a mother of A, B, C. So here the condition says that from one element of set A, it should be correlated with only one in the set B. So that is the condition of a function. But there can be another condition, like for example, it may so happen that two different elements in the set A can end up with the same value. In other words, we can go to a marketplace, and when you enter a shop, you will realize that biscuit, though it's a different thing, and bread, though it's a different thing, their value may be same, 10 rupees. So it is possible. The only thing that we need to keep in mind is that the same biscuit should not give us two different value, rupees 5 and rupees 10. That is not a function. Likewise, the very good example that I can give is sometimes called 1-1 function, and it is attendance, taking attendance in the class. Each member in the class is assigned a unique number. So roll number 1 to one individual, 2 to another individual. So this is actually function. And when there is a unique distribution in such a way that each element is assigned a unique value, it is called 1-1. in the first example, when the biscuit and bread is having the same value, it is called many one. So likewise, we can have different classification of functions. But let us look at an example of some relation. Let's say when R is having a member 1, 3, 2, 4, 5, 1, is R a relation? You can say yes, because here you see that 1 is not repeated. I mean 1 is having a unique value 3, 2 is also having a unique value 4, 5 is also having a unique value 1. So it satisfies the condition of a function. So in order to understand this function, we can come up with more vocabularies. Just like we have tried to understand relation in terms of domain, codomain, and field, even here in function, we can talk about domain and range, or values, or codomain. So the function is always defined on an element, so that the element can be uniquely assigned a kind of value. So that when it shows up in an ordered pair, the first element will be always a member of domain, and the second element is always a member of the codomain value. So we have just seen domain, codomain, or range values, but also unlike relation, this is just for the purpose of convenience. When we are defining relation with the help of symbols, we are using capital letters or uppercase, like capital R, capital P, and so on. But in the case of function, we will use the lowercase, the small letter. That is the conventional practice in the set theorem. Now I've mentioned that function is a very special case of relation, and I have also explained that relation are a very special case of set, because they are the result of operating two different sets, which we call it Cartesian product. So that means we can also use the same kind of set theoretic operation like union and intersection to even talk about functions. But because of want of time and space, we will not be able to talk about all those different operations on function. However, just like relation and converse relation, we can also talk about an interesting property of function. Function, converse function, and inverse function. When both f and its converse, means converse function, are also function, the converse is called the inverse of the function. So when the converse of a function f is a function, that is, the inverse of f exists. The inverse of s is denoted by this symbol f minus 1. So with the help of these definitions like functions, converse functions, and inverse function, we can actually do some operations or some kind of formal reasoning, for which we may have to look at the board again. When the inverse of a function exists, we have the following identities. That is, 1. On the left hand side of the equation, we have inverse function of x is x, and number 2, function of the inverse function of x is x. That means if both sides, function and its converse functions, are also function, then these two equations are possible. Given a function, we may find its inverse by using these identities. For example, we can do these derivations. Let a function of x is equal to x minus 5, and then we will do the numbering 1. Then substitution, we can substitute the rule of substitution, substitute inverse function of x by x. So both the side you substitute. Every occurrence of x is to be replaced by inverse function, because we have seen that they are equal. Now if that is done, we can have function of inverse function of x on the left hand side, and on the right hand side inverse function of x minus 5. So using 2, the above equation we have seen 4, using 2, that is function of inverse function of x is x. Now we can have this step, x equal to So the whole thing has been replaced, left hand side has been replaced by x. X, keep in mind, is coming from equation number 2. Now on the right hand side we have done nothing, so the same thing, it's still the same, inverse function of x minus 5. The next step is, now if they are identical, we can change the position. This is commutation. So bring the whole left hand side to right hand side and right hand side to left hand side, and then finally the equation we have is inverse function of x is equal to x plus 5. We go on to another special type of function, and this idea also we got it from the relation. We can talk about combining two relations in one. Like we have three elements, x, y, z, and then two type of relation. If x is related to y and y related to z, then we can show relation from x to z. Just like that, in function also we can talk about two functions to pick out a unique value. So we call them sometimes composition of function or composite function. Let me give a technical reading. The composition of function means using two functions, let us say f and g, is expressed as f o g or f of g of given argument x. So in equation, function of g is also function of x, is equal to f o g of x. So now we keep looking at the screen. Suppose we have a function set of functions like f, g and h. We can find functions like f of g, h of g, or h of f of g, means more and more functions, and so on. That means we can keep on having more and more complex kind of function. Perhaps we keep looking at the screen, we can explain with the help of one example. Let us try to find the function g of f given the argument x, given that. So step number 1, keep looking at the step because steps are important. Step number 1, we are saying function of x is equal to 2x plus 3. The next step, let's say function of g over x give us 5x. Now in the step 3, by virtue of step number 1, we will have this g of f over the argument x is equal to g and 2x plus 3. How did we get this one? It's because of the definition of composite function. Once we have this equation, you look by virtue of, I said, keep looking at the steps. So in the step number 3, with the help of step number 1, we have derived this equation. The next, on the left hand side, it remains the same. Then on the right hand side, by step number 3 and step number 2, we can derive 5 of 2x plus 3. Ultimately, what we get is 10x plus 15. So coming back, you see, given a function, we can generate more and more functions, and a function is to help us pick a unique value. So if we don't know the value of a certain number, we can use a lot of functions and then find a unique value. To use as a small example, addition is a function. So 5 plus 6 is an addition of is a function of addition. Together I can say plus 5. See, now I'm using another function, plus 5. Again, it can give to certain argument but certain value, but before I go there, on the left hand side I can still give another function, say plus 8. Now all these are function adding one by one, and on the right hand side I can give a unique value. So this idea of function actually help us to understand the language of mathematics, or so to say, that is where we are coming to our main important focus. This is language of logic. It is with this that I want to conclude this module on set theory. How do we understand theory, set theory in relation to logical theory or logic? It is this that set theory provides us with powerful tool or call it language, so that we can understand modern symbolic logic. When we study logic, we see it as a kind of language. So logic will be the language and set theory will be the meta language. In other words, it is in the language of set theory we are going to understand or explore the language of logic. So they have this interesting relation between set theory and logical theory. That is why the importance of set theory as a tool for studying logical theory or modern symbolic logic. Thank you.